While we work in Spark, or more specifically PySpark, a common consensus is use built-in functions. Avoid user-defined functions, that is UDFs. But why? Is a UDF really that bad? And here is the question that bothers me. What if I create my own function and somehow put it inside PySpark.sql.functions, which I'm sure you must be aware of? Would Spark finally understand it? Let's understand all this and much more in this video. What you see on the screen is just a normal user-defined function. Python knows exactly what to do with it. What you see now is the version that we write for Spark. A UDF is basically our way of telling Spark, I have some custom Python logic. Please apply it to my Spark data. But wait, did you notice what I said before? We are talking about PySpark. Why do we need to specify Python here? Because PySpark is Python's interface of Apache Spark. Spark itself is primarily built on the JVM, while PySpark lets us interact with Spark using Python. Let's see another example of UDF and its equivalent built-in function approach in PySpark. See, Spark already has hundreds of built-in functions, but it can't possibly have every business rule your company will ever invent. That's why UDF exists. You must be thinking, if both approaches produce the exact same business result, why does Spark prefer the second one? To understand this, you need to focus on the flowchart depicted on the screen. And to understand this flowchart better and get the answer of question that I asked, let me take an analogy. Think of Spark as a huge restaurant kitchen. You are a customer. You give the restaurant an order. And the journey is roughly, you place the order, restaurant understands what you ask for, it creates the cooking plan, head chef optimizes the plan, kitchen decides who does what, and food is actually prepared. Basically, when we use a Spark built-in function, we are not simply calling a Python function and getting a result. We are constructing a Spark expression. This is where Catalyst enters the picture. If we write a code like what you see, Catalyst doesn't need to understand the Python implementation of upper because upper has been translated into a Spark native expression. And if you want to verify it, you can use .explain method. Notice what Spark's plan contains, a native upper expression. The output you are seeing in Spark's query execution plan broken down into its different stages along with a note about Photon, which is native vectorized query execution engine of Databricks written in C++. It is designed to speed up heavy large-scale data processing. Because our data frame is a tiny local collection, that is local table scan, Spark routes it through its standard execution engine rather than invoking Photon. For small or local test datasets, this is completely normal and expected behavior. You will only see Photon fully light up when working with large distributed tables. Anyway, the important thing is that Spark understands this as a Spark expression, not an arbitrary Python function. Now let's focus on its UDF equivalent. Here, as I use explain method, you can see that Spark knows that a Python UDF exists, but it doesn't see x.upper as a Spark native expression that it can reason about. See, standard Python UDFs require Spark to serialize rows from JVM, that is Java Virtual Machine, into Python, process them row by row in a Python worker process, and serialize them back. To make this fast, Databricks uses Apache Arrow for vectorized high-performance data transfer between Spark and Python. With Spark 4.2 release in July 2026, we have much better use of Apache Arrow for UDFs. Without Apache Arrow, Spark would have to serialize every single row into a standard Python object, that is pickling, which is quite slow.
That is why Python UDFs are generally much slower than native Spark built-in functions. And if you want me to reiterate, the reason is UDFs force data out of Spark's native JVM engine into Python, causing serialization overhead and preventing Spark from optimizing the execution across large distributed clusters.
Think of it like a node. When it is a built-in function, Spark reads, Mr. Spark, make this column uppercase. And when it is a user-defined function, Spark reads, Mr. Spark, execute whatever is inside this opaque envelope. So, in terms of UDFs, Spark knows there is a function here, but it doesn't know the implementation inside the envelope. And there is a common misconception that Spark knows nothing about UDFs. Actually, Spark does know some things about your UDF. For instance, when you write at the rate UDF by passing string type as parameter, what Spark knows? It knows there is a Python UDF, its expression inputs, its return type, that is string here, and certain UDF metadata. What Spark doesn't know? It doesn't know how your Python algorithm works, how to rewrite it natively, how complex internal branching logic is, and whether it calls external systems. And that is what we mean when we call a UDF opaque to catalyst. As you see on the screen, when it comes to UDFs, Spark has additional work to move data between Spark's execution environment and Python. That doesn't mean every Python UDF is slow. It means there is an additional execution boundary that Spark native expressions don't have in the same way.
When I try to test the difference between runtime of a built-in execution logic with a UDF for a simple operation on a 10 million rows, I clearly saw a minor difference. As you see, first I have brought 10 million rows and created a simple operation on it. With built-in functions, I got output in 0.379 seconds. Whereas when I use the same approach for UDF, it got completed in 0.544 seconds. But don't forget that in distributed environments, 10 million rows are quite normal to process, and actual difference between a UDF and a built-in function will be visible while working on even higher count of rows. Okay, but what if I want to use this UDF in Spark SQL? Can I use it directly? No. As you see, if you try to refer it in your SQL query, it will throw error. So how to fix it? You need to register this using udf.register, as you see on the screen. Once this is done, you can use your UDF in Spark SQL. But keep in mind that this registration solves a different problem of using it in Spark SQL. It gives SQL access to your function. It does not turn your UDF into a Spark native built-in function. Now comes the crazy question. What if I put my function inside PySpark.sql.functions? What I mean is, if you see last two lines depicted on the screen, if I do something like this, would that make Catalyst understand it? No. Putting a Python function in a namespace doesn't change execution semantics. We could monkey patch or wrap Python objects all day, but Python namespaces are not equal to Spark's expression system. If we want our function to become an official built-in function in Apache Spark, then we need to implement the functionality according to Spark's architecture, test, API, documentation, and review process, and ultimately getting it accepted into Apache Spark project by creating a pull request. But if we simply want to extend Spark in our own organization, Spark also provides extension mechanism. As you can see on the screen, Spark Session Extension is an extension mechanism that allows platform engineers and enterprises to inject custom functions, rules, and strategies directly into Spark SQL the moment a Spark session is initialized. Instead of manually registering UDFs in every notebook or script, you can use extensions to automatically load company specific UDFs globally across clusters, or scoped dynamically to specific sessions.
So, when should you use UDFs? Let's take a balanced approach. We can use UDFs when rules genuinely cannot be easily expressed via built-in expressions. For example, proprietary credit risk scoring, customer classifications, and this falls under complex business logic category. We can also use UDFs when we rely on external specialized packages that Spark has no native equivalent for. For example, specific scientific computations or advanced NLP libraries. And this falls under specialized Python library category. In conclusion, never use UDFs is a wrong statement. You can use a UDF when you genuinely need custom Python logic. And always check if a native expression can do it first. So that's all I wanted to discuss in this video. If you liked it, please hit the subscribe button. Thank you.